Hi, my name is Jesse Chick. I'm a vulnerability researcher with Trellix, and I'd like to walk you through a solution to my favorite challenge from our second annual Capture the Flag. This challenge is called Skeleton Key. It's worth 400 points, and you might remember that it incorporates both a web component and a bit of binary analysis at the end. So let's jump into it. Okay, so the description that you're given for this challenge is the following. Catmen has stumbled across a website for a piece of medical software in the canine labs. Our intel suggests this medical software is being used on mummies excavated near the last known location of a piece of Anubis. It can't be a coincidence. Unfortunately, she doesn't have a valid key to unlock all the features. Catmen needs you to procure a key to unlock the fully featured software. Okay, and then there's a note about how the key itself is the flag. You are also given a bunch of previously used keys that are now invalid. So this is nice, at least it gives us the format of the keys. And of course, although it's not linked here directly, you were also given this web client. Okay, which it looks like it can only really do one thing, which is validate a key. So if I were to put just whatever in there, it says, yeah, okay, invalid key format, fine. If I now return to my terminal and grab one of the keys that I know are in the right format, let's see what happens. Oh, well, it takes the format, but it still says invalid key. I suppose that's to be expected. Okay, so let's do some initial poking around here. When you pop open the source for the HTML, a couple of weird things sneak out. There's this doc type tag directive, however you want to describe it, that's in like the very middle of the file. And it looks like what follows is an entirely valid HTML file unto itself that's kind of been like embedded in this web page. That's a little weird. Probably worth making note of. Another thing that's interesting here are these comments. So it looks like this is a commented out warning for an undefined variable in this file. That's worth copying out and keeping for our records. Not least because it also almost guarantees that this server is running Linux. It also gives us some knowledge of the file structure. So definitely worth keeping in mind. The second comment here is a note to remember to log keys checked to log file in skeleton key. All right. So more knowledge of the file structure at play. Again, at this point, we're just gathering information, seeing what the developers have revealed to us. I don't see anything super interesting inside the HTML, so let's poke around with the inspector tool. Already checked out the elements. A blank console means everything loaded correctly. All right. Not much in the way of sources either. We have index, which is blank. That's kind of weird. And then an impressively boring style sheet. Okay. If we go over to the network tab, I'll have to refresh. Yeah, we see that there are only 2 sources loaded, nothing really interesting from the style sheet. But if you take a look at the HTTP request headers for index, we'll notice that there are a couple of cookies being sent. This first one seems to just be like a session key of some sort. Second one, I have no idea. But this last one is quite decipherable. It's called template, and it has the value header.php. Well, maybe this explains the weirdness that we're seeing in the HTML. Maybe this sort of subfile that's been embedded in the HTML is actually sourced in a different file called header.php. Just a thought, right? But it's a really easy assumption to test, because we can just use a cookie editor here to give that cookie a value that of a file name that's almost certainly not going to exist on that server. And then refresh the page and see what happens. Ha-ha! We've got some warnings. All right, let's pick this apart. So it's attempting to include templates /ASDF ASDF, which is a non-existent file. Okay, so this is PHP's way of including other source files. So it's attempting to open that file, include it as content, but of course it doesn't exist, so it gives us that warning. Okay, well, the next thing that we might try here is to figure out, well, where does that header file sit in the overall file structure? We know that index.php exists at this path, but where is header? Well, the hint is actually given within this warning, because if we notice that the include statement is trying to include from template /ASDF ASDF, we realize that templates is itself a folder that exists in the same directory as index.php. So that's another good piece of information to have. We now know of the following path. And this can be easily verified by modifying this template cookie to pop up one directory, do a bit of a directory traversal there, and then go straight back into templates and select header.php. Now this should work because these sort of constitute inverse operations in this context. So if I save this, we should see the web page just render correctly. And it does. It's still giving me the invalid key, but that's not a problem. At least we didn't get any of those warnings. Okay, well that's good to know. So now we know that we can use this cookie to do directory traversal on this server. And we can at least attempt to leak contents to the screen. But in order to do that, we're going to have to specify the valid name of a file on this server. So what are the other files that we know of? Well, we know of index.php, but that's the source file, so that's not much good to us right now. We know that there's a header.php, but that's also would be the correct usage, so that's not terribly interesting. That leaves this skeleton key.log file. So if I wanted to try to include that inside of the PHP within index, I would need to set the cookie to something like, well, let's see, if we're within templates, if that's the current context, then I need to pop up out of templates, up out of HTML, up out of www, and then into log. And specify skeleton key.log. So that should be the next cookie that we try. Save that, reload the page. Ah, interesting. Okay, so we see that in place of this header, the Dr. Leets or Dr. Trav's Leet software or whatever, we see key checker program activated, current working directory keygen, waiting for user input, invalid key. And we see that repeated a couple of times. So I think it stands to reason that what's happening in this case is the contents of skeleton key.log are just being dumped straight to the screen. So that's great. So we get this as a repeating pattern. So key checker program activated. Well, that's nice. We know the name of another file, and we also know where it is. So getting more and more information about the file system there. So if we were able to leak contents to the screen in the previous fashion just by specifying a file name, it stands to reason that we could do that with just about any file on the file system, including this key checker file. So why don't we test that hypothesis? In this case, cookie would look like this. We got to pop up out of templates, up out of HTML, and then into keygen, and you specify the file key checker. That should cause key checker's contents, whatever they are, to be dumped to the screen. So save that cookie there and then refresh the page. And we see a bunch of disgusting binary printed to the screen. It looks like this is an executable. We can see the ELF magic number here that suggests that this is a Linux executable. And that's great. But I would really like to be able to take a look at this file as a binary. And I really don't like my odds of just being able to copy and paste it directly from the web browser. So it looks like we're going to have to get a little bit more creative if we want to be able to save this binary locally. Well, you can go into your inspector tool, look at the network sources. Oh, shoot. If I want to view it, I'm going to have to modify the cookie again. There we go. So one cool thing that you can do with the inspector tool is you can export specific requests as like curl commands. So I just copied this request as curl. Now I'll head back over to my terminal here. And as you can see, it's just tracing out the full request, but I want to save this to a file. And specify output keychecker.html. If we take a look at keychecker in a hex editor, we notice that we're starting out with just normal HTML, so far so good. But then we quickly get into this just gross binary data that couldn't be rendered in the web page. Okay, so the next step is to snip out the bit that we care about. Specifically, the binary part. But that's kind of sitting in the middle of this blob of ASCII that constitutes the rest of the HTML around it. So the first step is going to be to figure out where the binary information starts and where it ends. So I'll walk through this here with a little bit of care. So it looks like the binary information itself starts right here. That's the ELF magic number. So that is occurring at an offset of, okay, we got 40 in hex plus 7 by the looks of it. So the binary starts at 47 in hex. And then where does it end? I have to scroll down a little bit. And there we go, there's the bottom. So it looks like the first non-binary-esque byte in this file, reading top to bottom, is this new line. So I would imagine that this would be a good place to stop our chopping. So that's occurring at 28,000 in hex and 20F by the looks of it. Yeah. Okay, so now we have our offsets in hex, but unfortunately, if we're going to use the dd command, which is sort of the canonical way to cut pieces of a file out of one and then save it into another, then we're going to have to convert these, all of our values to decimal. So I'm just going to open up my trusty built-in calculator here. And I'm going to punch in following just to get some idea of how big that chunk is, regardless of where it sits inside of the surrounding HTML. So here we notice that 47 in hex is 71 in decimal. So that's something that's good to make note of for our DD command in a second. And we don't actually need to know the end. What we need to know is how long that chunk is. So the length, in this case, is whatever the difference of these two values is. And it looks like it's 10,216. Okay, fantastic. So from here we can start to craft our DD command. So I want a DD with a block size of 1. My input file is going to be keychecker.html. My output file, I think I'll just call it keychecker. Seems like that's the name of the binary itself, on the server anyway. And I want to skip the first 71 bytes. Make sure I don't grab any of that HTML. And then I want to grab a total count of 10,216 bytes. So it looks like that worked correctly. And we can tell, boom, there we go. We have keychecker. So let's try to run this. Oh, permission denied, of course, yeah. I have to give it permission. And now when I run it, it says 1 argument is expected. All right, I can play ball. It didn't like that, invalid key format. Well, that looks familiar. What if I go to key history, grab that key again? That should get us further into this binary, shouldn't it? Cannot open log path file. Well, that's interesting. At first glance, I have no idea how to get around that. So maybe it might be a good idea to do what probably is most people's first step. Wasn't mine in this case, but running strings on keychecker. And when we run strings on keychecker, we get a lot of interesting results, actually. Straight through the middle of the output here, we can see a bunch of stuff that was probably programmer defined. So there seems to be a local path to a file called data. The local path there, a bash command. Oh, there's a bunch of good stuff here. I'm just going to copy all of the stuff that looked like it was programmer defined. And we notice that one of the strings is logpath.txt. Well, that seems like exactly what's being referenced here when the program is saying it can't open a log file. It's probably lamenting the absence of logpath.txt. So let's check that assumption. If I just touch a file called logpath, it should change our output here a little bit. Now it just says cannot open log file. Maybe it's trying to read the contents of logpath.txt and is unable to. Maybe there's like supposed to be a path in there, that would make sense given the file name, that contains a path to where logs are meant to be written. This is probably not the log file itself, so I can just, echo, literally anything into log path, and that should do the trick. Okay, so now it's getting mad at me and saying it can't find data. So it looks like there's another file called data that also has to be present. So let's touch a data file. And when we do that, it gives us a different message, but now it says secret flag file.so file too short. Okay, well clearly it didn't work, but we're definitely homing in on the flag. That's great. So at this stage, I think it might be a good idea to try and see if we can recover what the original data file is. Because we need to get past this point if we want to get the flag. The secret flag file.so, which is that being created? Oh, it is. Look at that. This file obviously can't be too short if we're going to get the flag. So maybe in the same fashion that we're able to leak key checker from the front end, we can also leak this file called data. So let's give that a shot. I'm going to be using here pretty much the exact same cookie. Except this time, instead of key checker, we just want to grab data. We've done everything right. We should see just a bunch of data pumped to the screen. Nice. That looks like base 64, which reminds me of a command that we spotted in here. Okay, that's fantastic. Great. Now, it may not be necessary in this case. Copy and paste might be sufficient for this step, but I'm going to go ahead and use the same method that I used to kind of snip out the binary chunks of keychecker.html to grab this data file. Now, I'm going to use the exact same means that I used before. I just won't go through the exact calculation of all the numbers, since the process is going to be entirely identical. So first things first, I am going to export this request as curl. And I'm going to specify the output file as data.html. Great, and it looked like that works. So, like I said, not going to do the calculations, but I will show you the dd command here to snip out the data. Ooh, took a second there. All right. So now we have a file called data, and by the looks of it, it is ASCII text. And that makes sense, it's base 64. Okay, great. So now we should be able to rerun key checker and have everything work out just fine, and maybe even receive a non-1 exit code. Perfect. Okay, it just said an invalid key. So that means we've done everything right except for give it a valid key. So what to do next? Well, you know that this key checker file ultimately has to be doing some kind of comparison. It's building up some secret flag file.so, which perhaps contains some string, the key, the flag, that is ending up alongside our argument here in like a string comparison. I think that stands to reason. So one strategy here for figuring out what the second operand in that comparison is, the flag in other words, would be to figure out exactly where that string comparison is being done and then put a breakpoint on that instruction, the one that invokes stir copy, and then just dump the contents of the registers at that point using GDB. So I think that that's what we'll go for here. Now, one thing that we're going to need to know, well, there are a couple things that we're going to need to know before we're able to make this actually work. But the first thing that we need to know is where this process is being loaded in memory. So one way to do that, there are a number of ways to do that, but the way that I'm going to use is to start GDB. Oh, it looks like I've already done this with a different key. That should be fine. And to just use the command start I, which is just going to break on the first instruction, and then to go over here and figure out what its process ID is. So this isn't the correct process, that's GDB. Instead we want this process. So key checker is sort of being run inside GDB in this case. So we need this process ID, and now I'm going to cat out the process memory map. And that should tell us where this thing's being loaded. So it looks like the base address is right here at a bunch of 5s, followed by a 4, followed by some 0s. This is our base address for the running process. This is critical because we need to know exactly where to put the breakpoint. Now we need to know where the instruction that invokes string compare, or however the comparison is done, where that exists in memory. So we can put a breakpoint on it. Now to do that, I'm going to use a program called IDA. I already have key checker up here. IDA is a reverse engineering tool. You can use your reverse engineering tool of choice. It doesn't really matter. I just like the way IDA renders this. So this is key checker, pretty much. It's a pretty short file, or it comes from a pretty short source file, one would have to imagine. And this is the main function. So looking around here, we see a lot of familiar strings. We see invalid key format. We see things like too many arguments applied, 1 argument expected. This is just kind of outlining the conditional logic used to make sure that the key's in the correct format and that all of the necessary support files are present on the system. But once we get past all that, we get down here. Notice that, there is a string compare here. It's sitting right here, and depending on the result of string compare, the message is either going to be master key found or invalid key. Well, that seems pretty conclusive. Now we also know that the offset from 0, since I didn't bother to rebase this binary, is 1314 in hex. So offset of strcomp is that guy. So this means that we need to set a breakpoint at the sum of these two values. I hope it's clear why. Over here, I'll just go ahead and set that breakpoint. And now I can just hit continue. And if everything was done correctly, we should have broken at string compare. And we can see in the output here from Jeff that indeed we have. We effectively found and set a breakpoint on string compare. Now the operands that are being used are being stored in RDI and RSI. I made note of that when I was looking in IDA. And we notice here the string that we supplied as an argument on the command line. We also see in RDI this unfamiliar key-looking thing, which is the other operand. Well, I have a hunch that that's the flag. So quitting out of GDB for a second, let's just take it back to basics here and run key checker, but with this key. And if our assumption is correct, that this is in fact the flag, then key checker ought to spit out a positive message, as opposed to invalid key. And so it does. Master key found. Enter the key as a flag using the format ATR. So now finally, at long last, we can assemble our flag, and there it is. Okay, so I hope that you enjoyed that. I hope it made sense. I hope that the pace, rhythm, and timing was congenial. And we look forward to doing more videos like this again. We'll see you next time.